Good day, everyone. My name is Denis Shishin. I would like to thank the organizers of the COM 2023 conference and my co-authors for the opportunity to present our research. The topic of the presentation is experimental study and thermodynamic analysis of high-temperature processing of mixed nickel-copper sulfide feed. The work was done in Pyrometallurgy Innovation Center of the University of Queensland in collaboration with Anglo-American. Let's first explain why fundamental work is needed in this area and then talk about the main components of the project, which are thermodynamic modeling, targeted experimental study, plant data analysis, and application of the results towards understanding of recovery of metals and stability of operations. I don't think there's a need to explain how important are nickel and copper and platinum group metals for the technology, energy, and our future. So let's focus on the process, which is delivering these metals, and think how to help make it even better. Anglo-American process is essentially a mixed nickel-copper sulfide smelting. The platinum group metals concentrate in liquid matte, which is slowly cooled and crushed. Since the matte is sulfur deficient, during the cooling, metallic nickel-rich phases precipitate out, and PGMs preferentially concentrate in those metallic phases. They can be separated magnetically and further processed. So, nickel and copper and small amount of cobalt are valuable byproducts. The first pyro step is electric furnace, which must operate at very high temperatures due to the presence of magnesium oxide. At this step, most organic materials such as magnesia, silica, alumina, calcium, and chromium are separated from matte, forming liquid slag. Matte is then further processed to eliminate iron in the next unit, which is oxidizing Anglo-American converter furnace. It operates at low temperatures and produces matte suitable for slow cooling. But the slag in this furnace contains significant amounts of droplets and dissolved nickel. To increase the recovery of metals, this slag is further processed in electric slag cleaning furnace. Slag cleaning furnace produces additional amounts of matte, which can contain PGMs, and it is returned either to smelting furnace or to the converting furnace. Thus, in spite of different temperatures and oxidizing reduction conditions, the process is largely controlled by slag-matte equilibrium thermodynamics. Within the nickel, copper, iron, oxygen, sulfur, silicon, aluminum, calcium, magnesium, chromium chemical system. The typical questions to improve the recovery and throughput involve maintaining the balance between temperature and formation of solids, relationship between the initial nickel to copper to iron ratio in the feed, process parameters, and final matte properties, and questions of minimizing the losses of nickel, copper, and PGMs into the slag. The purpose of thermodynamic calculations is to predict at least three things: the conditions of formation of phases, liquid or solid, the distribution of elements among those phases, and energy balance. Good thermodynamic models can do those three things simultaneously using the Gibbs energy minimization algorithm. And FactSage software can do that very well. But the accuracy of such predictions will depend on how accurate are mathematical models for the Gibbs energies of all potential phases within the chemical system. FactSage has very good models. We use modified quasi-chemical model for slag with two sublattices and quadruplet approximation. For liquid matte metal, we use the modified quasi-chemical model with one sublattice in pair approximation. And for complex solid solutions such as spinel and olivine, we use the compound energy formalism. But the accurate predictions with these models still depend on experimental data used to establish model parameters. To fix the model parameters, we apply the Kalfat methodology, which requires producing a single set of model parameters, which describes as wide as possible data set of experimental data of various type. A set of model parameters is called a thermodynamic database. During the development of the database, we often see a lack or contradictory literature data to fix certain model parameters. In this case, we design in-house experiments to resolve the problems. In practice, the process of development large thermodynamic database is continuous and iterative. In previous 20 to 30 years, a number of commercially available databases has been developed, and they resemble a little bit a building. Predictions in multi-component systems are based on firm foundation in one component binary and ternary systems. But what if an update or improvement is necessary in the foundation? Those improvements are often not done or postponed because they require huge number of dependent systems to be reassessed. Since 2021, we try to create more flexible, even agile type of the database development system, which is learning by feeding on new experimental data. We achieved significant progress in these directions, but still need a bit time and resources to finalize it. Today we will show a small part of experimental data generation step, which will be used in the development of the database. Let's have a look at the experimental methodology using an example of the nickel-iron-oxygen-silicon-sulfur system. The method of choice in our lab is equilibration, quenching, electron-probe microanalysis technique. The typical experimental steps include designing experimental conditions using FactSage calculation, the choice of mixture and holding material. In this case, we use the silica substrate. After several equilibration trials and after studying the samples, we select an appropriate equilibration time for a given range of temperatures and expected phases to form. After equilibration, the samples are quenched in brine to preserve the composition at high temperature. They are mounted in epoxy resin, polished and coated with a layer of carbon for electron microscopy. The compositions of phases in equilibrium are measured by electron-probe microanalysis after the equilibration, so that the experimental data produced is valuable even when small changes in bulk composition happen during the equilibration. In this case, we found that studies in literature were focused on equilibrium at high partial pressure of SO2, but we were interested in conditions of equilibrium between slag, matte, and iron-nickel metal, which corresponds to low PSO2 and sulfur-deficient mattes. On the next 3 slides, we will look at the experimental results compared to literature data and to thermodynamic model predictions. Results of the present study are shown using circles. In these diagrams, the x-axis corresponds to the concentration of nickel in matte, which we are trying to increase during the process by removing iron sulfide. So, on this diagram, the concentration of iron decreases as a function of a nickel in matte. The other 2 diagrams show the partial pressure of SO2 or O2 for these conditions. We even have the experimental data from literature by Font in 1998 to confirm the oxygen partial pressure predictions. So thermodynamically speaking, the removal of iron from matte is achieved by increasing the oxygen partial pressure. So what about the other elements in matte? On the top left diagram, we can see that mattes in equilibrium with metal contain less sulfur compared to conditions at high PSO2, which is confirmed by literature and reproduced by the thermodynamic model. In case of equilibrium with metal, sulfur decreases monotonously, whereas at high PSO2 it goes through a maximum. The maximum is caused by the significant solubility of oxygen in mattes near low nickel region. The results of the present study are also projected onto iron-nickel-sulfur triangle, which clearly shows the sulfur deficiency when compared to the FeS nickel 3s2 stoichiometry. Now, we can analyze the results for the same equilibria conditions in terms of slag composition. Very important parameter is the true chemical solubility of nickel in slag. It increases with increasing concentration of nickel in matte. Both experimental data and thermodynamic model predictions indicate that slags at high PSO2 conditions dissolve more nickel compared to the case in equilibrium with metal. The concentration of sulfur in slag is important because of the sulfidic mechanism of solubility of nickel in slag. In the modified quasi-chemical model, this mechanism is realized through the introduction of nickel-containing quadruplets. The most important one is iron, nickel, oxygen, sulfur. There is a discrepancy in the model predictions and literature data for the high PSO2 conditions. We recently reproduced those experiments, and even not shown here, the preliminary results confirm the model predictions for nickel and sulfur in slag for the high PSO2. The next important step in the project was the analysis of the plant samples. Together with Anglo-American Platinum, we developed the protocol for sampling. The samples were delivered to Brisbane, and we used the SEM to study the microstructure and electron-probe to measure the compositions of phases. The most important were the observations for slags. In the case of smelting furnace, the slags are fully liquid, with very few droplets of matte and almost no spinel crystals. The slags from the converter furnace contain significant amount of spinel crystals and more matte droplets. The slags from the cleaning furnace were mostly free from spinels, but the remaining crystals were often associated with matte droplets, and we concluded that they may interfere with the settlement of the remaining matte droplets. The simplified process model, based on FactSage equilibrium calculations, described well the trends in slag, in spinel, and in matte compositions. Of course, the plant data samples showed a range of compositions, especially for spinels, but the compositions of observed spinels followed the oxidation reduction path as predicted by the model. FactSage calculations also provided the process conditions such as oxygen and sulfur dioxide partial pressures, which cannot be measured directly, but were useful for further analysis. Improvements in the stability of freeze lining are very important for the stability of operations and throughput. Freeze lining is a stagnant layer of partially solidified slag, which protects furnace walls from corrosion by molten phases at extremely high temperatures. It is achieved by active cooling of the furnace walls and controlled by the heat flux as well as solidification properties of slag. An example of mathematical model predicting the thickness of frieze lining is shown on the slide. We can see that the model requires an important parameter, the temperature of the stagnant layer where frieze lining is stable. In earlier studies, this temperature was often selected to be just the liquidus temperature, but later it was demonstrated that the temperature is between the liquidus and solidus. More accurate value for the frieze lining temperature can be obtained by better understanding of percent solids in the slag as a function of temperature. Let's demonstrate that it is not as simple as a half distance between liquidus and solidus, as was suggested by some authors. In the course of this project, we demonstrated how to calculate the liquidus and the percent solids in the slag. The results of plant sample analysis and process modeling were used to specify the conditions for the calculations. Due to the presence of chromium in the slag, the liquidus is extremely high, but the percent solids just below the liquidus temperature increase very slowly because the solids are basically chromium-based spinels. Only when olivine starts to precipitate out, the combined percent solids are significant enough to maintain the stable frieze lining. The current hypothesis is that at least 50 to 70% solids in the slags are required to maintain the stagnant layer. These diagrams show that melting the last remaining droplets of spinel crystals can be very challenging. It can be more important to control the input of chromium in the slag cleaning furnace than to try to increase the temperature, if the purpose is to prevent the formation of the mashy layer. Mashy layers form on the surface between slag and matte due to the intermediate density of spinels. It interferes with the settlement of matte droplets. To conclude the presentation, let me stress the importance of fundamental research in improvement of the stability and efficiency of pyrometallurgical processes, such as mixed sulfide smelting. Doing the projects like this require expertise and laboratory studies, development of process models based on thermodynamics, ability to analyze the plant samples. Also, it became evident in the recent years that the projects like this must be complemented by professional education activities. The implementation of the results requires a good understanding of pyrometallurgy by process engineers and furnace operators on site. We are now trying to fill in the gaps in the university education systems for pyrometallurgy. I would like to express a sincere gratitude for the continuous support by industrial sponsors. The pre-competitive fundamental research financed by the consortium of companies worldwide made it possible to win Australian Research Council linkage grants and preserve the Pyrometallurgy Innovation Centre during the times when Australian universities were shutting down the metallurgy programs. Many thanks to Dr. Rodney Hundemark from Anglo-American for permission to use a portion of the results as a showcase study.